In this class, we'll discuss some interesting consequences in which third law works. So what we have seen so far is that in third law, every action has an equal and opposite reaction. So if one object pushes on another object, then the second object also applies an equal and opposite force on the first object, which means also that the two forces are acting on different objects, and therefore if an external force is applied on an object and it is the only force that is applied on the object, then both objects should accelerate. Unfortunately, when we think about situations, we are not able to see the acceleration of both objects. It is not directly imaginable because frictional forces always act. Like, say for example, if you attempted to push a wall and you say that where is the wall accelerating, or where am I accelerating? If you push hard enough, you will accelerate, but the wall doesn't accelerate. So you may say that I don't see the consequence of the third law in this. But actually, if you are able to think of situations in which you eliminate the support force or the frictional forces that are operating in these cases, then you will see that third law works in a fairly peculiar manner. And really speaking, those examples are actually not very rare. It's just that you have to look at it a little bit more carefully. So we will take one peculiar consequence of this third law, which is when, let's say, somebody jumps down from a table. So there is a table which is at a certain height, okay, and there is a person on this table who is going to jump. Okay, as the person is falling, right, the person falls because there is a force of gravity that is pulling him down, which has the value of mg. We know this situation fairly well. But then the third law says if one object is being pulled with a certain force, then the object which is pulling this object will also be pulled up by the same force, which leads us to a very peculiar situation. That is, if you think in terms of the earth, let's say, drawing circles is one of the most difficult things with this. Okay, take that to be the earth. Okay, and so oceans. And say this person is jumping down to earth somewhere over here. Of course, I can't show a scale diagram, but the person is falling, let's say. Okay, I mean, by this scale, this person will be something like 600 kilometers tall, but so the diagram is not to scale. Okay, not to scale. But we'll use this instance to understand what happens. So presumably this person is falling down to the ground because of the attraction of gravity, and that force is of course directed towards the center of the earth. Okay, now you can argue that since the person is pulling the earth is also pulling the person, or to put it the other way around, you fall because gravity pulls you down because the earth has gravity. So therefore you must also be applying an equal and opposite force on the earth. So why is the earth not accelerating? Now, if you examine this situation, you have to say that if second law is indeed a law, then the earth has to accelerate. Okay, so your acceleration in this can be calculated if you find out the ratio between the force and the mass, right? Acceleration is equal to F upon m. The force is equal to mg and your mass is m. Okay, so therefore you can see that m divided by m becomes 1. The acceleration is equal to g, which has that value of 9.8 meters per second per second. Now let us come to the earth. Can we find out the acceleration of the earth by using the same second law?
Yeah.
Of course you can. That will be acceleration of the earth will be equal to the
You
force
have to know the mass
divided by the mass of the earth. Okay, and this should give you by how much you actually end up accelerating the earth when this happens. All right, now you can notice something peculiar over here. The force, of course, we know it is equal to mg, if you like minus mg, because you're pulling the earth in the opposite direction. But the mass of the earth is a very large quantity. So can somebody just refer the textbook or quickly tell me what is the mass of the earth? It's there in the last page of your textbook.
Yeah.
Found out?
Yeah, so it's 5.972 times 10 to the power 27.
I'll
10
take,
to the power 24 on Google.
Yeah, 24.
you're Googling it. Yeah,
That's
24. That's right.
27.
24. Okay. Now, the thing is that uh, the mg over here is your mass multiplied by the gravitational constant. So if you take an average class 8 student, let's say her mass is about 40 kilograms. Okay, it's you're staying at home, so your average mass will now go up to 45 kilograms, multiplied by g, which is, we can take it as an approximate value of 10 newtons per kilogram, divided by this huge peculiar number, which is actually 598 followed by 22 zeros: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22. Okay, now you don't need to do the math. What you need to tell is the value of this acceleration on earth going to be big or small?
Small.
So very small.
It's going to be very, 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 very small, right? Because, okay, you have a 10 here, so you can get rid of 1 0. Okay.
How did you get minus 45?
No, I just kept it as minus because mass cannot be minus, but the force can be minus. If the earth is pulling you down with a value that is plus mg, then you are pulling the earth up by a force which is minus mg, which has to be minus mg. Both can't be mg.
Shouldn't the mass be this 5980000?
Sorry.
Shouldn't the mass of the earth, since
Yeah.
mg, so in mg the m should be 5980000.
The m is, yeah, but this is mass of the earth, not the force. So that's why, I mean, I don't know what exactly you're saying, but yeah. So coming back to this, 45 divided by 598 must be something like 0.9 something. Okay, because this is almost 50. If you keep this as 50, and in fact, why don't we turn that into 50, because it will be convenient, because it's just a rough value, right? So let's say that people have been eating a lot because they are staying at home, and because of that, their weight average weight went up to 50 kilograms. It's usually about 40 kilograms when you're in school. So if you look at this number, you will get something like 0.00000. I'm forgetting to count now. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 blah 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 9. Okay, and that is the acceleration experienced by the earth, meters per second square. No wonder that you actually are not able to see the effect of this acceleration. But every time you jump down from a step, or you step off the footpath on the road, you are accelerating the earth by that incredibly small value. And it cannot be so that it does not happen. It has to happen because of second law, right?
So won't it happen?
Won't it happen? Yes, questions.
So there are like so many people on Earth. Okay? There are 7 billion people on Earth. Okay. Now some of those people might be sleeping at the moment, but then so many of those people would be doing some activity, right?
Yeah.
So every single action they do, like in 1 second also there can be multiple actions.
Yeah.
Okay. So won't that actually amount to some
Yeah.
like
Yeah.
in
Yes,
some number?
it is.
Multiply
Matter.
that by a few billions and you will get it, but that will still be a very, very, very small.
Exactly. So the
I
thing
think
is again the same thing that we discussed last time about the internal forces in the book, all the molecules moving about in random. It is possible that out of the almost I think maybe some more than 7 billion people on Earth today, chances are that maybe even a few millions are able to coordinate a certain action. Maybe a million people are stepping off the stepping off a ladder or a pavement or jumping off a table at any given point of time. But you see, they are doing it at different parts of the Earth. You get it? So the effects of all their accelerations tend to eventually cancel out. But what you can do, as I think Ishan was suggesting, is if you can collect, let's say, a billion people in one side of the planet, okay, and make them all jump up and down in a coordinated manner, then yes, it is possible that you will significantly accelerate the Earth out of its orbit. In fact, you don't have to do that. Let me just finish this. In fact, you don't have to do that. There are geological processes that end up doing that. Do you remember the
earthquake.
tsunami that happened in Indonesia
Yeah.
in 2001? Right? During that tsunami, it was an undersea earthquake that took place, because of which the tsunami was triggered. The undersea earthquake actually loosened several million tons of soil, which then fell into a cavity. And when that happened, obviously because of gravitational pull, it happened. So therefore, the amount of soil also pulled the Earth. So scientists geologists then calculated that the Earth's orbit around the sun shifted by a very, very fractions of millimeters, but it did get shifted. Okay, so geology gives us the proof for something like that happening. Yeah, now those who want to say something can say.
Yeah, sir, I want to say something. So there is a way that we can like accelerate the
Sorry,
Earth.
what?
So there is a way that the humans can like somehow accelerate the Earth, right?
How?
Which you just told, this one.
Sorry?
Which you just told, the like
1 billion
flood
people.
the people on one side.
Yeah, but that would be a logistical nightmare to do. But yes,
Still,
Sir.
the number
you
is
can actually
big.
calculate. If you take a billion people, see, billion is how many zeros? 9 zeros.
Yeah.
Okay,
Yeah.
and 9 zeros multiplied by, even if you take the average weight of an individual to be 100, you add 2 more zeros. So you are going to end up with 11 zeros at the top, and there are 22 zeros at the bottom. Still, your acceleration is going to be minuscule.
Yeah.
Yeah.
Sir, it was there in the What If book.
Sorry?
It was also something like this, that if you gather people in the world
Hmm.
and then make everyone jump at the same time,
Yes.
then what
Exactly.
would happen?
So if you do it with, see, a billion, whether it is 1 billion or 7 billion, is still going to have 9 zeros. So the zeros in
Yeah.
the numerator is not going to increase by much.
If
So
only the mass of the
is
Earth was
going to be
less.
extremely small. Okay.
I can't even imagine this big number. Like I can't. I can just see the zeros, but it's not amounting to anything in my head. It's so big.
Yeah. That's the kind of thing it is, with very large numbers and very small numbers. But okay, we
So
don't have to go this far. Although this is an interesting situation to think about, we don't have to go this far to look at situations in which this kind of an third law application takes place. We can think of far simpler ones, but I'll take out one more peculiar one. Okay, let us say um, that you are at a riverside or something like that, okay, and you happen to be on a boat. Okay, so you're standing on a boat, a very small boat as it turns out, and in your hand you have your puppy. I don't know what that looks like. Okay, it looks like a bird. Okay, right. So what you do is you need to drop your puppy. Okay, I'm embarrassed by this puppy, so I'm going to change its head a little bit so it looks more like a dog. How do I do that? Oh God, it looks more like a bird now.
Sir, I'm confused. Where are the eggs and what are the
Okay,
humans?
okay, I think I'll leave it at that.
Just make the
All
triangle
right.
views.
So now, how do you do that? You need to put the dog on the, throw the dog onto the shore. So you have to obviously apply a force. Okay, force 1. That is the force that you are applying on the dog to make it, to push it, to accelerate it so that it reaches the shore. Now, obviously, the dog is going to apply an equal and opposite force on you. Otherwise, there is no chance that it is going to accelerate, right? So F2. And we say that these two forces are equal and opposite to one another. So what will happen is, because of the force that you exert on the dog. So let's say the mass of the dog is md and your mass is m whatever y u. Okay. So mass of y is more than the mass of the dog, obviously. So therefore, the acceleration that you are going to experience, your acceleration is going to be less than the acceleration experienced by the dog. So the dog will land on the ground and your boat will go backwards. And if you are not ready for the boat going backwards when you do this, you might lose your balance and fall into the river. Do you see that situation happening? Do you understand what I'm trying to say?
Yeah.
Okay.
Even if the boat is tied to a stump on the shore, you will still fall.
You sound like something like this happened to you. Yeah, the precise thing is, if it is tied to the shore or somebody is holding the boat, then you're not going to experience the third law's effect. So that is why I created this situation where you'll experience the third law's effect. Exactly the same thing happens when you try to step off the boat. If you're not used to boats and you're standing on a boat, right, and you try to step off the boat by jumping off the boat, what's going to happen is that the boat is going to go backwards and you're going to fall where you are, because the acceleration experienced by you is going to be far less than the acceleration experienced by the boat, and then you will again fall into the river. So that is another interesting consequence of the third law. So when you are getting off boats, small ones, not very big ones, because big ones have a lot of mass, so the acceleration will be small. But if you're getting off small boats, don't ever jump before the boatman tells you to do so. Okay. Because the boatman will hold the boat and he'll ask you to get down and he'll say, don't jump, get off. Okay. Yeah. Any questions?
So basically, the person is throwing the dog down into the water. I don't understand.
Basically?
So basically, the person is trying to push the dog down or onto the.
The down part doesn't matter so much for our discussion. Yeah, of course, that is also going to happen. The person is going to push the boat downwards, so the boat will bob a little. That's not the issue. The issue is the part of the movement which takes the boat backwards. That's the one that is going to cause the problem for you. Okay?
Sir,
Yes.
so see, that's why the boats move, right? When we row backward, it gives the opposite push and then the boat moves forward.
Correct. Yes, exactly.
Okay, wait, I have a question. So, suppose we gather all the people from Earth and then they all push on Earth to jump, okay?
15 minutes back, okay.
So and when they push on Earth, Earth
down.
will accelerate, right? But when they are in the air, the Earth will again deaccelerate, right? So it will be in equilibrium again.
You might end up cancelling the effect. Yes, I kind of understand what you're saying. Yeah. Okay, so then we come to more routine discussions of application of the third law. There are two examples that I want to take up. Yeah. I'm sorry, I'm not able to hear you.
Sir, I got disconnected in the middle. Sir,
Yeah.
what is the system in this boat example?
The system is just the person with the dog and the boat. So the forces are internal, these two forces. So what happens is, if you look at the system afterwards, okay, since you asked that question, I'll just briefly mention that. Let's take the situation a little bit later. And what is happening is that the dog has, oops, should be black. The dog has accelerated to, it looks like a monkey, okay, has accelerated towards, I mean, in the forward direction. And you have accelerated in the backward direction. Okay, so if you take this whole thing as the system, okay, now this whole thing is the system, right? So now what is your question?
Sir, if the dog's out of the system, then why is the dog still in the system? As in,
No,
the
no,
system was mainly
it hasn't,
connected
it
to the
hasn't
boat,
yet
right?
hit the ground. So you can say that the motion of the system as a whole has not changed. So you can say that the velocity of both, velocity of the system was equal to 0 before. Okay, so since this is a system and the forces are internal, is the velocity of the system, the new velocity of the system, we say v prime, this means prime, afterwards. Okay, so this is the velocity of system before was 0. That means the dog and the person were not moving. What is the new velocity of the system? If there were no external forces being applied, then the new velocity should also be equal to 0, right? But there is a contradiction. What is the contradiction? The dog has a velocity in the forward direction and the person has a velocity in the backward direction. So you say, hey, so the system is, so this whole thing about the system does not work. But if you think about it, the system's velocity is going to be 0 because the dog's velocity, if you take it as positive direction, the person's velocity will be negative, and therefore the momentum of this system is going to be conserved. That's something we have to discuss in the next class, but since you asked the question, I mentioned the word momentum. That's a new animal. We will talk about this a little more in detail in the
Oh my god.
next chapter. Not actually the next chapter. No, it is the next chapter. Yeah, it is the next chapter.
Sir,
Yeah.
but sir, so this person is applying the F1, the red arrow,
Yeah.
is an external force. No, it's not an internal
No,
force.
no, no. It's an internal force. How is it external?
Sir, because the person is pushing the dog onto the shore.
Correct there, but I am taking the system represented by the brown line as both the dog and the person.
Yeah,
and
that's what I'm saying. So shouldn't the system be dog separately, person separately?
that's entirely your choice.
Ah.
You want to look only at the dog, then it is perfectly fine. So I can create a new system over here because you are interested only in the dog for some reason, must be an animal rights activist. So you look at only the dog.
Yeah.
So then you say that the force F1 is external force to the dog.
Ah.
Then you can say that, okay, then what happens to the dog? Since there is an external force applied, it has an acceleration. No
Okay.
problem.
Sir, but one question I have. So in the same system, can there be movement? I mean,
Within the system, there cannot be any movement unless an external force is applied to the system.
so then there's movement here.
Exactly, that is the confusion. There is movement, but you see the movement of both parts of the system. The dog is moving in the forward direction, the person and the boat are moving in the backward direction. So the net movement is still equal to 0. But we can't discuss it like that. I'm not quite being correct when I say the net movement is 0. I should say the net momentum is 0 but that we will discuss in the next chapter. So keep this as a
Uh-huh.
question for the time being. We will take it up again in the next class. Okay.
Sir?
So let me move on now, otherwise I won't be able to take up the two examples. Those who have any doubts or questions about this, hold on to it. We'll discuss it after the class is over. Okay. So let me just finish up whatever I was trying to say. A few good examples to talk in terms of application of third law. One is, oops, I don't want this color. One is when you have a cannon and a cannonball being fired from the cannon. Okay, so here's the cannon, and there's a cannonball inside this. Okay, and you use some gunpowder. There is a blast, and the cannonball moves forward, and the cannon goes backward. So when the charge inside this, basically it will be some kind of a gunpowder, blasts, then what is going to happen is there is going to be a pair of forces. Okay, what is that? The cannonball is going to be pushed forward. Okay, and therefore it will experience an acceleration in the forward direction. But at the same time, the cannonball is going to apply a force backwards on the cannon. So you keep this as F1 and you keep this as F2. So what will happen as a result of this is that both the cannonball and the cannon will accelerate. Okay. So if you take a sort of fiduciary line, a line that does not move basically, the cannon is going to get pushed backwards and the cannonball is going to get pushed forwards. Or should I put it in a different way?
Different way.
The direction of this I should change. Okay, so
Rasam smoke.
Yeah, this is moving in the forward direction and this is moving in the backward direction. Okay. Another straightforward example is, and many of you might have tried this out, you fill a balloon with air and then you release the balloon. Okay, so there is air inside the balloon.
Yeah, sir, it goes all around.
Yeah. And when you release
Childhood
this,
favorite.
what will happen is that
The air escapes and the balloon goes up.
the air escapes and the balloon starts moving.
Okay. It goes in the opposite direction of the air.
It goes in the opposite direction of the air, exactly. So what is happening in this case is, see, when the air is inside, what it tries to do is it's trying to apply a force outward. The air particles are trying to apply a force outward, but there is no way for the air to go out.
They're trying to escape.
Yeah, they are trying to escape. Okay. But when you create an opening, we call this as an orifice. When you create an opening, an orifice, then what happens is, now there is a possibility for the air to escape out of here. Okay. So the air comes rushing outside. Okay. So what is the air pushing against in order to accelerate? The air particles are accelerating. So what is it pushing against in order to accelerate?
The balloon.
Surface of the balloon.
The surface of the balloon, exactly. So these arrows are not correct. The surface of the balloon. So they are pushing against the balloon like this, which creates a net force on the balloon in this direction.
Sir, aren't they going the other direction to escape?
Wait. Okay. What about the forces in this direction? Well, they are going to get cancelled by forces that are acting in this direction. The only place where they won't get cancelled is in this direction because the air is rushing out. Okay. So the air which is coming out is experiencing a force in this direction. This is the force on air. And this one over here is the force on the balloon. So because there is a net force on the balloon, the balloon is going to start accelerating in this direction. Okay, and exactly the same concept is used also in rockets. When we launch rockets into space, some of them have boosters and things like that. So basically what happens is that there are gases inside this. Usually it won't be inside this part, but inside this part. Okay, and those gases are burnt, and when they are burnt, they expand and they come out in this direction.
They move faster.
Right?
And
gases are these?
And because of this, what is going to happen is that there is going to be a force on the rocket which is in this direction, right? And the gases are experiencing
gases are
in
these?
this direction. So this force, which is the force on the rocket, accelerates it forward. So these are some of the examples by which third law makes things happen around us.
Sir, the gun, the cannon one, the same thing happens with the gun also, no?
Exactly the same thing happens with the gun.
Yeah, except smaller.
And you can then say, if between the gun and the bullet, which one should have a greater mass, and what will happen if the gun and the bullet are of the same mass? Okay.
It also depends on the person, right?
Sorry?
It also depends on the person who is holding the gun, right?
Yeah, the person's weight also contributes towards the weight of the gun. But anyway, when we discuss momentum again, those questions will come up. We will discuss it further at that point of